All right, back by popular demand, rapid integration by parts. So here we go. Rapid integration by parts is essentially when you have a integration by parts problem that requires you to do integration by parts within integration by parts. And what I mean by that is if you just do your classic UDV, du and v, and you set x cubed, 3x squared, you've got sine x, you've got negative cosine x, and you bust out your formula, which is uv minus v du, you would get negative x cubed cosine x, right? That's u and v, minus the integral of v du, which would be minus cosine x, 3x squared. And what can be kind of a hassle is that now within this, you have another integration by parts. And this could happen, more than once. And the good news is if you don't understand integration by parts or you don't want to learn another technique, you could just crank out another, integration by parts, set up a new u, a new dv, and kind of go from there. So this video, or the two examples I'm going to do, are just kind of an additional supplemental, kind of a shortcut that picks up on this fact that you might have to do this a couple times. And if you kind of want to spoil it, if this is u and this is du, then the idea here, I might have wrote it backwards, but the new u, right, the new u, if you had to do this again, is the old du. And so you can kind of pick up on that and maybe cut down the work a little bit. So let me get back into it. Let's do this example full speed with rapid integration. So rapid integration, I'm going to cut some corners here, and I'm going to essentially have a column on the left, and in this column, I'm going to take the derivative just a bunch of times. And these are like all my u's, all my u's and all my du's, so to speak. And over here on the right side, I'm going to take antiderivatives, meaning the antiderivative of sine, and then the antiderivative of negative cosine, the antiderivative of negative sine. And you have this, this natural stopping spot when you run out of derivatives. And then I'm going to put some arrows here. And you can think of these arrows as kind of like every time you have a u times a v, but above each arrow, I'm going to alternate signs because the original formula, plus minus, kind of alternates signs. And so if you think about this, these two as being kind of your first sets of u and du, and on the right side, v and dv, I can go into the first term, which would be, negative x cubed cosine x. It's the product of that. And then as it turns out, the next product is going to be my next term. If you are wondering where the plus sign came from, it's the double minus. It's this minus and this minus. I don't want to leave that on there. And it comes from the minus up here that I'm circling, and then you'd have like a minus inside the argument if you're kind of working this out by pausing the video or maybe slowing it down, but those two minuses would end up becoming a plus. We're capitalizing on the shortcuts. The next term, believe it or not, would be that product, which would be 6x cosine x. And then the next term, you're seeing the patterns. The next term would be this, minus 6 sine x. And then the last term, essentially, down here, underlining it nice and thick, the last term is where you would have like the last integration by parts. So this really has all of these. It would be like if I had to apply integration by parts. It looks like 4 times, but it's getting kind of sloppy. And so at the very, very end, I'd have this integral, right? Talking about this integral of the product of 0 times sine x. You know, this is my last du. This is my last v. Maybe you want like subscripts or something. My 4th v, my 4th du. But check this out. This is really the integral of 0. And the integral of 0, dramatic pause, insert dramatic pause here. The integral of 0 is where you have maybe your plus c or something. So this is a quick way to get that integral. All right, follow-up question, slightly harder. The other scenario where this works kind of nice, but you have to, again, proceed with caution, is let's do one more. So let's go e to the x, maybe cosine 2x. And so it's very easy maybe to jump into setting up integration by parts or rapid integration. And then if you don't think about it for a second, you could get in this hole of, hey, I'm just going to take the derivative a bunch of times, down here. I'm going to take the antiderivative a bunch of times. But with a question like this, you could end up writing forever because cosine's derivatives just keep alternating, cosine, sine, and e just goes forever. Whereas this one had kind of a natural stopping part. And so my fear with some of these shortcuts is you can't use it every time. You got to pick and choose kind of what the best technique is. That is the challenge, right? Picking the right technique. So if I do the derivative with the chain rule over here, again, antiderivative, and then I, again, antiderivative, derivative. I don't know why I'm putting the 4 at the end. I should write it out in front. But again, you can see this could get ugly quick. So let me show you how this plays out because I like to keep these videos short. But I'm going to do rapid integration like I just demonstrated. You've got a plus sign, you've got a minus sign. But I'm actually going to stop it here. I'm going to put a little plus sign. And as we set up the answer, I'll show you why that is. So this integral is equal to the product of e to the x cosine 2x. That's my u and my v, or my first one. And then the next product, I just circled it, would be plus e to the x times sine 2x times 2. I like to put those coefficients out in front. And then, if you're tempted to do more arrows, you'll end up getting in kind of this infinite loop. And what I want you to see is that you can stop rapid integration whenever you want. And this last term would be, it looks like there's a 4 there, so you'd have something like this. The key thing with this is realizing that the original integral kind of showed up in the question. And that's what we're looking for. That's how I knew from experience to stop there. Again, this is only the case where you have this potential problem of them going on forever. All right, so here's the fun part where you get to kind of nerd out. If you think of this integral, this one right here, as an equation, it equals this expression with an integral in it. I'm going to change the color to add some dramatic effect here. If we treat this like an equation and we add, oh my goodness, we add 4 cosine 2x e to the x, and we add it to both sides. I don't know why I put the plus sign there. Add 4 of these. Then we really have one of them, right, the original plus 4, we really have 5 e to the x cosine 2x's. Over here, they cancel out. And so all we're left with on the right side is 2 terms. And the very last step, again, our ultimate goal is this boxed integral. And if I want to get that integral by itself, booyah, I'm going to divide by 5. And what we got is this original. And then you can make the whole thing over 5. You could make these 1/5. You could leave it how it is. You know, maybe you want to write it a different way, just for fun. Or maybe you want to keep it as 2 separate terms. So many fun things about math. You know, expressing your answer the way you want to express it. And then don't forget your plus C. All right. Hey, that's the bell. That means this lesson's over. I hope that you guys have a great rest of your day. Thanks for watching.